would like to introduce you to our first speaker, and that is Juan Cruz. I was so very excited when I read Juan's bio and heard about what he was going to be briefing on, because he, in my opinion, has worked on some of the most exciting projects that we have ever done at NASA. So Juan is from Puerto Rico. He went to MIT for his undergraduate work, and Virginia Tech, where he got his PhD in aerospace engineering. And he worked on the Mars rovers that we sent to Mars back in 2004, Spirit and Opportunity. And his current and as many of you well know, one of those rovers is still going, although it was originally determined to be only a 3-month duration. And the other rover, I think, lasted 7 years. So we can truly look at that as one of NASA's success, and they're generating lots of invaluable data for us. And we're getting ready to launch a new rover, 2012, is that correct? It's launching this year. And it's Opportunity, and that's Juan's current project. So I want to have you join me in welcoming him to the podium. I know he's going to give us a really interesting speech about what's going on with his projects and how he's usually modeling a simulation. So Juan, thank you very much.
Okay. Well, good morning to our friends out in Mountain View, and good afternoon to the rest of you. I wanted to start this presentation with the very basics about modeling and simulation. And the bottom line is that I want to go to Mars. Okay? If I could have one thing to tell you, I would say I want to go to Mars, and I would walk out. Although that's not quite right. I mean, I don't personally want to go to Mars. Some people do. I don't. But what I want to do is actually go there through a surrogate. And the surrogate has a name, and it is being completed right now. And the screen just went blank. There we go. It is being completed. It just got shipped to Cape Kennedy, and it is the rover called Curiosity. This is a significantly larger rover than the ones we have sent before. Just to give you an idea, Spirit and Opportunity were roughly the size of golf carts. Curiosity is the size of a Mini Cooper, okay? And it's about 1,000 kilograms of mass. Now, we're not going to send it there the way you look at it there. It kind of gets folded in this mechanical origami, and it gets placed into an aeroshell, which is shown here, which is also at the Cape. I know that the people off-site won't be able to see the pointer, but basically the aeroshell is divided into the heat shield, which is the bottom black part here. That's going to protect us from the heat of entry. Then there's the back shell, which is, as you can imagine, the back side of the aeroshell. And then in here, you also see the crew stage, which is what's going to get us to Mars through our 8.5-month trip. The whole thing gets stacked up. So you see the rover here. It's folded up. It is somewhat, besides being significantly larger than Spirit and Opportunity, it also has a very important difference, which is that Spirit and Opportunity were solar powered. And thus, we had all kinds of issues with the season of the year and dust, etc. Curiosity is actually nuclear powered. It has a radioisotope thermal generator. You see it back here, which should give us a much longer life. And basically keep us away from having all these worries about the sun power. So here we have the rover. It's attached to a descent stage. I'm going to show you how that works. The whole thing gets packed together, sandwiched between the aeroshell that I've already shown you and the back shell. And then at the top, you put a solar-powered crew stage. And then you send it off to Mars. And what I want to do next is I want to show you how this all works, in particular, how the entry, descent, and landing works. For about 8 months, the spacecraft looks like this. You see it from behind, so you see the crew stage in here. And then we move forward. As we approach Mars, the cruise stage will no longer be needed, and it will be released right before entry. Okay? It did its job, it's gone. At this point, the aeroshell is traveling between 5 and 6 kilometers per second. That's a lot of energy. So as you can imagine, as we start entering the atmosphere, it's going to get really hot because that energy is being dissipated into the atmosphere of Mars. If we were to absorb it, the spacecraft would just simply vaporize. So what we do is we guide the spacecraft. You see the little rocket in the back. And we transfer all that energy to the atmosphere. People have spent years of their lives making that heat shield work. Okay. Once we get down to about 2.5 times the speed of sound, the capsule is not sufficient for us to continue decelerating. So what's going to happen is that a parachute is going to be deployed. Now, that parachute is going to be deployed while we're still going twice the speed of sound, or about 500 meters per second. So the parachute deploys, leads to a lot of load. At this point, the heat shield has done its job, so we drop it. This opens up the spacecraft, which now you cannot see in this animation, but then you get a radar coming on, and then it drops. And here's where the descent stage I showed you before. The descent stage has 8 engines. It slows the vehicle down, and it goes through a fairly complicated sequence of constant velocity and zero velocity descent. Here you see the radar is this portion here. The descent stage, in fact, on the rover, there's a little camera that's actually going to photograph the surface on which we are about to land. So later on, we will see the context of where we've landed. That's what's being shown in here. And then once we're pretty close to the surface, we're still not done. The rover now gets lowered on this bridle. The legs come out with all 6 wheels. And then the descent stage puts the spacecraft very, very, very gently on the surface. Then it has an important role to play, which is to sense that the rover has been placed on the surface here. The bridles get cut, and the descent stage flies away, and it's going to end up about several hundred meters away, and it's going to crash onto the surface. Okay. At this point, the rover's on the surface, the mast would come up, and we would be ready to start the mission. Okay. And this is what we call the entry, descent, and landing sequence. Now, as you can imagine, this is rather complicated. Okay? And if we were just to design the spacecraft and send it to Mars, the odds that it would succeed on the first try would be very slim indeed. But it won't be the first try. At this point, we are simulating this whole entry, descent, and landing sequence about 500,000 times per month. Okay? In the first 6 months, we've run 3 million simulations. And this will continue all the way till landing day. The rover departs from Kennedy come the day after Thanksgiving. That's when the launch window opens. And it should be at Mars in August of 2012. Okay. So this leads to the subject of the presentation, modeling and simulation. There is an end-to-end simulation of this whole process. This is an animation. This was created by graphic artists to look good. Okay, but there is, and they do a very good job, and we use these animations all the time, but it's just that, an animation. We have an end-to-end simulation that basically takes everything into account from the time the spacecraft touches the atmosphere to the time it comes to rest at the surface. Okay, and because we have a large computer bank, we can run about 10 to 20,000 simulations overnight, and we run that pretty much every night. So, with that introduction, I want to go ahead into modeling and simulation. Now, as I hear people talk about it, I kind of feel that modeling and simulation gets tossed around like candy, okay? And it's just jargon. And that really doesn't do it for me. So one of the things I want you to get out of this presentation is a clear definition of what is modeling and what is simulation, okay? Now, these are the definitions that we use here. But, so I can't guarantee you that they're universal. But it's very clear to me that this is what we do here. So first of all, a model. It's just a mathematical description of a vehicle's properties, either physical or an environment property. So here's a model of the aeroshell. So let me give you an example of a property that is a single number. What is the mass of this aeroshell on entry? That's a model. Okay? It turns out to be about 3,300 kilograms. You saw the parachute? How big is that parachute? It's just a single number. It's an area. But it's a very important number. Well, that's a model also. Clearly, there are more complicated models than that. For example, what is the drag coefficient of the aeroshell as it goes through the Mach number range from 25 to 0.5? Well, now that's a model. And that's a complicated model, and my colleague Mark Schoenenberger has spent the last 5 or 6 years of his life generating that. As it turns out, my job is the parachute models. So there's about 13 of them in the simulation, and I've been working on this since about 2003. Not full-time on it since 2003, but at least since then. So I want to define a model as some mathematical description of either the system or the environment. Notice that I also include environment here. So, for example, it's important to know what the acceleration of gravity is on the planet, on Mars. That has nothing to do with the spacecraft. Okay, the planet doesn't care about the spacecraft. But on Mars, it's 3.74 meters per second squared. So that's an environment model. We also care a lot about what is the atmospheric density on Mars. That's another environment model. Okay, so models. Okay, so then what is a simulation? What I call simulation is the combination of all these models and then physical laws in order to give us results that we are interested in. So, for example, we combine all these models in here. The parachute area, the parachute drag coefficient, the atmospheric density, the mass of the aeroshell, and here's the physical law, Newton's second law of motion. That's where the simulation comes in. So you assemble all this, and what you get is a response. In this case, it would be, how does the aeroshell decelerate? That's one of the many, many, many responses that are needed in a simulation such as this. As you can imagine, on the Mars Science Laboratory entry, descent, and landing simulation, there are hundreds, if not thousands, of models with thousands of parameters, and also thousands of responses that we look at. It's rather complex. So as I was going through this, well, I'm getting ahead of myself here for a second. So how does this all come together? Well, this is how I see it. We have the system models, aeroshell mass, aeroshell area, the environment models, atmospheric density, plus the initial conditions. We need to know where we start, okay? Where we start, how fast we start, okay? We pour all those into the simulation, which are the physical laws, and then from the simulation, we get responses, which are results of interest. Now, if you kind of look at it a little bit deeper onto this, and I realize that this is beyond your students, what I'm really describing here is solving differential equations, okay? And this is what modeling and simulation is all about, okay? It's, if calculus is the mathematics of change, differential equations are the mathematics of recursive change, okay? When something changes, but it then has an effect on itself. And one of the challenges for me in presenting this lecture is, okay, how do I describe something that involves, at its core, differential equations in a way that you can use to generate lesson plans for your students? And this is the best I could do. In a sense, this is a graphical description of what differential equations are all about. So, again, I think that asking your students to simulate the entry, descent, and landing of the Mars Science Laboratory is a little bit much. So what I tried doing was to come up an example of what would your students might care about. And here I just had to go back to my experience as a kid. That was a long, long time ago. But I was really into baseball, having grown up in the Caribbean. Baseball is king, okay? And here's the example that I've come up with. I want to hit a home run. And notice that I've already begun definition of my problem by defining some axes. And what I want to know is, what is the velocity and what is the angle at which the ball has to depart home plate, in order to get over a fence back here, as shown. Okay, what is that? So going back to the scheme that I've already presented, let me just kind of walk you through that scheme as applied to this problem. So first of all, we're talking about systems. Well, what is the system in here? Well, the system is very simple. It's just the baseball. Okay? And what are the system models? Well, for this problem, it's probably important how much this ball, how much mass it has. Okay? It's also going to be important what is the diameter of the ball, and also what is the drag coefficient of the ball. Notice that I've taken the problem one step beyond what is usually taught in high school physics, in which there is no aerodynamic drag. Now, as part of the materials I've provided, there's a long description, okay, step by step as to how you solve this problem. And then I'm going to leave it to you, the professionals, to turn that into a lesson plan. Okay, that is kind of beyond my ability. But that paper description that I've given you goes through the whole problem in both ways. And it starts from first principles. I start from F equals MA and take it from there. In addition, I'm providing you with an Excel spreadsheet that has both sets of examples totally programmed. And you can just go in and change the numbers and you can see what happens. So anyways, to get back on track, my system models are the mass, the diameter of the ball, because I'm going to be interested in the drag, and the drag coefficient of the ball. Notice I also have environment models, okay? The acceleration of gravity, okay? That's going to be important to this. And also, what is the atmospheric density? Now notice one thing, and this is my request to you. Notice that I have listed for everything 2 sets of units. Of these 2 sets of units, one is worth something, and the other one should be abandoned. Okay? So, spacecraft are designed in the SI system. Okay? Really, even though I have given it to you in both sets of units, really, this should all be done in SI units. Using customary units should be relegated to museums. Okay? But that's a much bigger fight than the one we can fight in here. And then finally, there's one more environment model, which is, okay, I want to go over this fence. Well, how far is this fence? And how tall is this fence? Okay? That's also part of the environment. So for example, the equivalent on Mars would be, where's that crater and how deep is that crater? Okay? So that's part of the environment. I take all this and I define some initial conditions. Okay? I'm going to say that I start at home plate at x equals 0. I'm going to say that, the ball's going to be hit about waist level, about 3 feet high. And I then need an initial velocity and an initial angle. Okay? And these are my initial conditions. And there on the bottom is just a cartoon of what this all means. The simulation is pretty straightforward. It's just Newton's second law, which still works for what we do very, very well, even for things like the Mars Science Laboratory. And again, in the write-up that I've given you, I start from there and move on from there. I don't sort of pull any equation, say, and then, this came down from the mountains, here it is. I start from Newton's second law. So the response of interest is, I want the ball to go over, okay? So what is the altitude when my position is over the fence? And that altitude better be higher than the fence. So that's my response. It's that y, okay? And then if that y, when x equals the fence, is my response. And what I'm looking for, okay, notice that what I'm looking for is actually not a response, is what is the combination of initial velocity and initial angle to get me that goal. So now you've seen essentially the problem set up in the way I've defined it, by defining a system, by defining the models, the initial conditions, the simulation, and what my response is. Okay, so it's the same architecture. And here are the results. And you can look at the results in the paper. You can play around with it. So here's one of the interesting things. I kind of knew this, but this really brought it out. Okay? If I get this initial angle, 45 degrees, and 196 feet per second, the ball will go over the fence, okay, on a ball with drag. However, notice how important drag is to this problem. That if you assume that it's no drag, you know, that ball is moving over to the next city. Okay, so notice how important the drag is to this problem. Okay, so that may be something that is of interest to your students. And by the way, you can probably see that this is a very general problem. It wouldn't be very difficult to change this into a football, a golf ball, or even a rocket with very, very little change. If any of you that are here at Langley are interested in sort of tweaking this in a different way during the 2 weeks you're here, just give me a call and we'll get together and we'll work it out. It should be pretty straightforward. Another way of looking at my response is this way. So again, here's white is the ball with drag, and what I show here is for any given angle, what is the initial velocity. So again, notice that for 45 degrees, I need about 196 feet per second. But if I assume that there's no drag, at 45 degrees, I only need about 110 feet per second. Okay? Is it clear? You see what I'm showing here?
I'm just recognizing the white curve is to the left of 45.
Yes, because it's not a parabola. And this is in the report. It's not a parabola. I mean, and you can think about, you can see it, you know, something that you hit, the drag's going to get to it, and eventually it's going to come down. You know, eventually it's going to come straight down. Notice that if there's wind, it's going to come up, and it could even come backwards. Okay? And wind is something I did not include in the description, but it's something that if anybody was interested in adding, it would not be difficult at all. Well, the optimum angle here is 45. The optimum angle here, it's about 40 degrees. Okay? Now, this is all well and good, but, you know, so how does it relate to the Mars Science Laboratory? Well, at the level that I look at it, it's essentially the same problem. Okay? You have a vehicle with mass. You know, it's a few orders of magnitude difference in mass, but it's still a vehicle with mass. Acted on by a gravity force and by an aerodynamic force. Okay? And then you have an initial condition. And from that information, then you can calculate a trajectory. In our case, we want to calculate a trajectory, and clearly it is rather more complex, to eventually put the rover safely on the surface of Mars. Okay? So it's essentially the same problem. It's just not, it's only different in the details. Okay? It's not different in the concept. To give you then sort of an example of what we do with the Mars Science Laboratory, this is old. This is like 2002. But here's the landing footprint. So here's a crater on Mars. You can see the contour plot. And then by running, and I'm going to talk about this in a second, Monte Carlo analyses, this is the probability of locations of where we may land. And here's our landing ellipse. Okay? We ran the simulation, I think in here it's a few thousand times. And here is where all those simulations landed. Now, a really good question is that, you know, it's all great and good, but tell me again, why is it you're running 500,000 simulations a month? Okay? I mean, can you do a few less simulations? Okay, well, let me come back to that. First of all, there's a lot of things we're not absolutely certain of. So on this problem, if we go back to the baseball problem, okay, what is the drag coefficient of this baseball? You know, I used a number in there. But, you know, is it an exact number? No, it's not. It is within a range, and there's an uncertainty. Okay? So there are uncertainties on the inputs. I mean, certainly there are also uncertainties on the atmosphere. Okay? That's number one. So the way we analyze this is by what we call Monte Carlo. We essentially try this value and that value and this value and that value. For this example of the baseball, I mean, about the only thing that is questionable is the drag coefficient, so there's only one parameter. But now think of a problem like the Mars Science Laboratory, where there's thousands of parameters, and all of them have an uncertainty surrounding them. So now you have to start trying many, many, many combinations of them. Okay. Number two, in here, I asked the question, what is the initial velocity and what is the initial angle to get me over the fence? Now, how did I do that? Well, I did it by trial and error. I mean, it took me several hundred trial and errors to get this curve. I mean, this represents several hundred runs, and yet it's a fairly simple problem. As you can imagine, in something like the Mars Science Laboratory, there's dozens, if not hundreds, of parameters involved here. So what is the optimal set of parameters that you want to use in order to make this landing safe? So here we have another set of possible changes. And then finally, in my baseball example, that fence is 400 feet away from home plate. On Mars, up until, well, still today, we're tracking 4 possible landing sites. So it's like, okay, you need to hit a home run, but in which ballpark do you want to hit it? Okay? We're hoping that within a week or two, we'll be down to 1 ballpark, and we just have to tell them what it's going to take to get a home run on 1 ballpark. But up until now, we have 4 sites. Okay? So when you do that, you end up having to run thousands and thousands and eventually millions of simulations. And this is the result of a few thousand in which the input parameters were changed. The drag coefficient of the air shell was changed, the drag coefficient of the parachute, the atmosphere changed. So when you look at the response, you don't get just one answer. You get a statistical value for that answer. Okay? You get a distribution. And those points could be all around here. Yes?
So going back to the relationship that you had between the angle and the velocity,
Yeah, here.
is that the result of a regression of collection of data points, and then you did something to it, or is it?
Well, I mean, it's a plot, but here's how I did it. I fixed the angle every 5 degrees. So I said 30, and I started playing with the velocity until, I got a home run. I moved on to the next angle. So I did it by hand. You could be significantly more clever about this, okay? You could create an optimization process. That was too much work rather than doing it by hand. Now, to bring it back to, again, the Mars Science Laboratory, that optimization on a problem that has so many dimensions is almost impossible. So we basically use a lot of engineering judgment. We run it, and we look at it, and we squint, and we turn our head. Then we have an argument in the office, and then we change it. Okay, so so the process is not all that different.
Yeah.
I mean, and very often we do things exactly like this. It says we say, okay, you know what? The value is somewhere between here and here. So let's just vary it over that range and see what the answer is over that range. Okay, so does that?
Yeah.
Okay.
Trying to find that in.
Yeah.
Can you explain who can no, not that subject. You just went to one more. Okay, so answer this for a kid. Who cares?
Who cares?
Clearly it's going to land in the oval.
Well, I care because first of all, it took a lot of effort to do that, okay? And number 2, here's the contours. The terrain is rising up. It's inside a crater. The terrain is going up pretty quickly. It's pretty flat in here. It's probably pretty safe in here. But if you mess up and this ellipse of points crosses over this point, over this region, your chances of crashing are pretty good. Okay? And notice that in the whole Monte Carlo simulation where we tried a whole bunch of cases, notice that there's a point that doesn't land. There's a point right there. Doesn't land in the crater at all. And those are outliers, and those things happen. I mean, sometimes something will go wrong. Everything will go wrong. So, that's Murphy's point. Okay? If it could go wrong, it went wrong on all the variables. And you end up out here, and those are outliers, and we know they exist, and, we don't ignore them. Very often when we get a failure, because this is just one response. I mean, we have tons of responses we track. We get failures. We take a look at those failures, and we track down what is the source. What is it that triggered that one failure. And very often it's one failure out of 8,000. And we will track it down. We'll hunt that down until we understand what is it that caused it to fail. And is there something that we can do to remove that case as a possible case? So this is why it takes so long and why we run millions of cases. Okay? So, to sort of wrap it up, this would be the summary of the whole presentation. The basics of modeling and simulation. First of all, we want to define a system, whether it be a baseball or the Mars Science Laboratory. We want to create the needed models. And the models need to be as sophisticated as they need to be to solve the problem, but no more. So for example, I can tell you that in the Mars Science Laboratory, we're not worried about quantum mechanics. Okay? Let's just say that Newton's laws of motion are good enough for what we do. Okay? There are no relativistic effects. We're not traveling near the speed of light. Okay? So you create the models that you need. You assemble the models and the needed physical laws into a simulation. You specify the initial conditions, which, by the way, it's another source of variability. On the Mars Science Laboratory, the navigation team is awesome, but they're only going to put us on top of the surface, on top of the atmosphere of Mars, sort of within a given region and at a given speed. They can't guarantee they're going to end up exactly in a particular place. Okay? And then we decide what are the important responses, and that's critical. I mean, you really want to make sure you're looking at the right thing. Okay? And which brings up the next to last point, is then you need to critically evaluate the simulation and change it as necessary to make it do what you do, and then you update and repeat as necessary. One thing, I think I have a few minutes, one thing that I wanted to show you that is not in your presentation, but earlier I showed you the an animation, okay? And it's a very good animation. When we run our simulations, okay, we animate some of our results. Clearly we don't have a catalog of 3 million animations, but sometimes it helps us visualize what we do, and this is one of them. And you will notice that it's a little cruder looking than the very slick animation than we had before, but it's an engineering tool. So this is an animation based on actual trajectory results. And here, this has been expunged, but in general, we have a whole set of instruments around the edge of the animation. This is just time. That allows us to see what is going on with the aeroshell. So here's the parachute sequence. There are some ballast masses that get ejected right before the parachute comes out. And then you'll see the animation pull out and the parachute comes out. You'll see the mortar cover first go out. There it goes. And then the parachute comes out. Okay. Things that you cannot see on the other animation, but we put in just to visualize it. Remember I talked about a radar? Those red cones, those are the radar beams. And we keep track of the radar beams because we actually have that contour map of the surface of Mars. It's actual data. That's not made up. Okay, so we investigate how the radar interacts with the surface. So, these are sort of engineering animations. The previous one is, to be descriptive. In a second, you'll see the rover comes down, etc. It comes down to two radar beams. It drops the rover on the bridle. The legs come out. And then it puts it on the surface, and the descent stage flies away. We have a lot of fun when we animate failures. Things that go wrong, it's like, okay, what happened? And then it's like, oh God. There was one I saw the other day. There was a cliff, and the descent stage just goes whoop, pow, right into the side of the cliff. Except that the cliff was not real. It was just a matter of the data. And then something that Jim mentioned that I just thought that I would bring in, something a little bit different and something that you saw today. I have been talking thus far about numerical simulations, but you can actually have physical simulations. And this, I don't do Mars all the time. Sometimes I do Venus. So this is a quarter scale model of a Venus lander. okay? And it's a dynamically scaled model. This model was placed, so here's the model. So in modeling and simulation, this is the model, okay? But the model by itself tells me nothing. Let me prove that to you. Results. Insight. I get nothing out of it. Okay, so the model itself doesn't give me a lot. But if I take the model and I place it in the spin tunnel, which you saw today, we actually then the tunnel is my simulation. So that's the model, and the tunnel is my simulation. And in a sense, you can think of this as an analog simulation. It's not a digital simulation. So here's the model flying in the spin tunnel last year when we were working on this proposal. And we were interested in certain amounts of responses and angles. The way we get data out of this is there's a series of dots on the bottom of this, and there's a motion capture system that tells me the motions of the vehicle. Anyways, that's all I had. I'll be happy to take any questions. I have just a few minutes. And I'll be available during the week. Any questions? Yes?
I was wondering if the Mars Science Lab, I understand 2 years ago they were talking about the spacecraft itself having landing position capability, as well as hazard detection capability.
That was a long time ago, and many, many dollars that never surfaced ago. It is guided, okay? So, for example, in the Mars exploration rovers, the uncertainty in the landing ellipse was about 70 to 80 kilometers long. For the Mars Science Laboratory, it's about 10 kilometers long, and it's guided. But what you're talking about is hazard avoidance, and that never came to be. That is left for a future mission.
We do have 2 sites connected, so you may want to see if any questions from our 2 sites.
Yes, and any questions? I don't know where I would hear it. It would just sort of be the voice of God would come down.
It will be.
Okay. Any questions at Kennedy or at Ames?